Welcome to the Tellerette Advantage. This is the first webinar in regards to the aftermarket business. Basically, Tellerettes are a major portion of the Verantis product line. All right, well, let's get rolling on this. So, the Tellerette Advantage. This is an introductory presentation where we kind of fill everybody in a little bit as to what the Tellerette packing is and how it works and what it does and why you might want to choose it. So, just to give you a little background, the way the Tellerette tower packing was originally developed, Tellerette tower packing in general is used to increase the intimate contact between a gas and a liquid to improve the absorption of a contaminant. Throughout the years, optimum packings have been designed to improve the contact area between the gas and the liquid to maintain the gas side pressure loss. Basically, you want the lowest pressure drop you can find. So a little background on how this got developed. The first towers were developed with crushed glass. It was as simple as putting crushed glass into a tower, and somebody said, oh, that works pretty good. So the next step was, all right, I've got this pipe laying around. Let's just see what happens when I put this pipe inside a column and see how it does for scrubbing. And guess what? It was better with lower pressure drop. So then we evolved into the saddles, which is getting into a more engineered specific style of packing. And then from there, it evolved in 1970. Dr. Teller invented the Tellerette, which was the first style of filamentous packing. And from there, we've developed various styles of the Tellerette packing all the way up to the current 3K design, which we use for our larger towers. So let's talk about the Tellerette. This is how the Tellerette works. Basically, the liquid is captured at the top. It is hit at the top of the Tellerette with inertial impaction. What happens from there, droplets form on these countless hold-up points. And then as the droplet falls, it strikes the next packing element, refreshing a fresh gas surface to the gas contaminant. This cycle continues throughout the whole packed bed, so you're always giving a new fresh molecule of water, let's say molecule water, droplet of water, to the gas surface. And contaminants are collected with various efficiencies at different packed beds. So the main thing that I'm going to push throughout this whole presentation is surface area is important, but it's not so much the surface area of the packing that's important. It's the surface area of the actual droplet of water. So basically what this shows, your typical droplet of water, let's just say, is 1,000 microns. And then what happens when it hits, it drops into 1,100 micron droplets. And guess what? You've now just got a magnitude of 10 greater surface area to absorb a contaminant out. So that's why it's so important. You may see saddles and they put a high liquid rate and they do the absorption on top of the actual saddle itself, whereas a Tellerette and other styles of filamentous type packing, the mass transfer is actually taking place in the airstream. So when it comes to scrubbing, there's basically two types of scrubbing that are most common. There's when we say scrubbing, that's called adsorption. So the first phase is pure phase. Basically what this means is that it's absorbed into liquid, into a pure liquid such as water. So ammonia into water is common. You can do HCl into water. You can do ethanol into water. Those are some of the more common versions. Then there's chemisorption. So chemisorption is just that, where you add a chemical into the water to enhance the chemical reaction. An example of this would be SO2 and NaOH. Now, I mentioned HCl in the pure phase. You can also do HCl with a caustic solution as well, or you can do ammonia with an acidic solution. It's not limited to one or the other. Different contaminants can actually do both. And more often than not, the pure phase, when it's just water alone, that's typically a once-through-water type scrubbing. So you got to know a little bit of background, the principles of mass transfer. The best way to describe mass transfer is looking at something that the majority of the people know in heat transfer. So basically, you've got your component, in this case, heat or mass transfer, over a unit at a time. Then there's a coefficient which is basically how well the transfer occurs. And then you've got, you need to know your surface area. And most importantly, you have a temperature gradient. Now, or temperature gradient for heat transfer. For mass transfer, it's a concentration gradient. Now, the best way we decide, one of the best, most common ways to describe mass transfer is that if you've ever put an onion inside of a fridge next to a glass of milk, naturally you're going to want to, naturally the scent of the onion is going to want to transfer into the glass of milk. So you can tell some form of mass transfer is taking place, and plus you don't want to drink that milk after the onion's been sitting next to it. So you know it's working. So each system has its own unique equilibrium. There's your operating line, then there's the equilibrium line, and then there's a slope in between, which will give you the number of transfer units. Now, where the slope is extra important is in this slide. We can show as the slope gets a smaller number, that basically means it's easier to scrub. So in this case, HCl, which is one of the absolute easiest components to scrub, has an extremely low equilibrium slope. As we go down the list, you'll see a component like HF is getting a little bit tougher. So basically, HCl can be done with water only, although we do like to add some chemical to it. HF is typically done with the chemical absorption. And then we go down to ammonia, the NH3. That's it can be done chemical. It can be done once through water. And then we start getting into chlorine and some of these more exotic compounds, which basically tell us that, okay, we've got to add a lot more energy to get the scrubbing to occur. And something such as like the CF4, that actually can't be scrubbed in a column. You'd have to use some kind of thermal destruction. So as you go through the list, it gets tougher and tougher to scrub for components. So when we're looking at designing a packed bed or utilizing the Tellerettes in an existing tower, one of the this is a list of components that we look at just to make sure our product is an equal or better fit for you. So we're looking at the exhaust flow rates, the temperatures and pressures, the contaminant type, because that's the worst thing we want to do is tell you, yes, you can do it with the Tellerette packing, and in reality, you really can't. The contaminant loading, so that way we can tell you what kind of removal efficiency to expect, and then the humidity of the gas stream. The required efficiency, that could either come from the client direct, or we can tell you what our product is going to do. So if there's a tower in the field that you know is getting 99%, you want to know how to get to 99.9%, we can look at a couple different functions on how the scrubber is designed, whether it be slowing down the gas flow, increasing the water rate, adding some additional height through like body flanges. There's a whole bunch of different ways we can address your situations. So this part of the presentation is where I touch on some of the different styles of packing that are out there. To do an equal comparison between packings, you really got to know what's available, what you may have, what your customers may have, what the client has in their towers. So the main thing to get through this is that not all tower packing is created equal. There are basically three types that we're going to touch on. There's the extended surfaces, there's the structured packing, and there's the filamentous style of packing, which is the Tellerette, the more engineered specific styles of packing. So extended surface packing, this could be in the form of the common saddles, the rashig rings. You see them throughout a lot more established chemical applications. A lot of applications that have kind of grown up through the 70s and stayed that way and have not gone into a new style of packing. And plus, it's something the customer is comfortable with. So some of the advantages, it works well with, of course, liquid distribution. So basically what that means is you can put a trough and let the water trickle down. You don't need to have even distribution across the surface area of the tower. And then more often than not, they're a low cost per cubic foot. Some of the disadvantages is that you have a much higher pressure drop, which also could lead to a much larger scrubber. So instead of cruising at 500 to 600 feet per minute, you may have to drop it down to 300 feet per minute or lower just to get the proper scrubbing efficiency. And like I said, it's a lower efficiency style of packing, and which means you're going to have a larger pack bed depth. So the example we have further towards the back examines a scrubber at 99% efficiency. So here's a couple pictures. The upper left-hand corner, that's your typical saddle. And then next to it, you have a high flow ring. And then you've got a couple other pictures right in the lower middle of the slide. So the next one I want to talk about is structured packing. The advantages of structured packing are that you have the highest throughput. Basically, you can crank velocity through this thing, and it's going to do the trick. And it's got a fairly low pressure drop for what you're doing with it. Disadvantages are your lower efficiency for absorption. Basically, you need the liquid film, and it forms some droplets. Typically, the structured packing is used in cooling tower applications where it's not as critical to do the mass transfer. We see a lot of it in that style of application. Typically, if we're designing a packed bed scrubber, we're not gonna look at utilizing structured packing. But we have also used our Tellerettes for cooling towers. So if your customers or you are looking for a better style of packing, we might be able to come up with a solution for you. So here's a little picture of one of the structured packings. So now on to the filamentous style of packing. So basically, this is your Tellerette. This is your Jaeger Tri-Pack, your Landtech Q-Pack. This is your Norton Coke Snowflake. So these are all the heavily engineered styles of packing. They're designed out there to do one thing, that's reduce pressure drop and maximize your scrubbing efficiency. So the advantages, this is basically a low pressure drop engineered scrubbing media, and it's going to create ultimately a smaller scrubber, meaning a smaller pack bed depth and a smaller diameter tower compared to your surface packing. You get high efficiencies, which also means you have a lower pack bed. And there's a relatively low cost. A lot of this is still a polymer-based scrubbing media, so you can get by with a lower cost product. Some of the disadvantages that you do require an even liquid distribution for best performance. What Verantis has done we have basically gone with a single spray nozzle in the middle of the tower. And what that does, that gives you even distribution across the whole surface area. Now that you can look at using weir trays, you can look at doing a whole bunch of different liquid distributors, but the key is just to make sure you have liquid across the whole surface area of the packing. So this is a picture of the Verantis Tellerette family. We started off with the number 1R, which is in the middle. Then eventually it developed into the number 2R for the larger towers. And then back in the probably mid-'80s to early '90s, they developed the number 3R for larger, taller pack beds to give you a little bit more structural rigidity. Then we had the idea of, okay, actually Dr. Teller had the idea of what happens if we put these little knobbies on the outside of the 2R? Guess what? It improved efficiency greatly on the pack bed. So the K on the 2K stands for knobby Tellerette. And then back in the early '90s, when Verantis' research and development center was going strong, there was the development of the number 3K packing. And basically what this did, this filled the void of the 5-foot and larger packed towers. Instead of using a whole bunch of number 2Ks, now we can put in the number 3Ks, and we've got lower pressure drop with about equal scrubbing efficiency as the number 2K. So it's a great packing on the market right now, and we definitely design every one of our scrubbers with one of these styles of packing when we can get away with it. So some of the other styles of filamentous packing, like I touched on, was the Rashid Jaeger Tri-Pack, which is an excellent form, another excellent style of packing, and we compare very equal to that brand of packing. Then we go with the Landtech, Landpack, and Q-Pack. And the Q-Pack is another great style of packing, and they tout their pressure drop, which we can't, we can come close to it, but they've got us beat on pressure drop. But we've got them beat on efficiency. So it's a matter of which which one's most important to a customer. And then the Coat Glitch Snowflake, which is another great style of packing. So as I touched on earlier, we talk about the surface area of the packing. Is it important? Absolutely. But guess what? It's not the packing surface area itself. It's the surface area of the liquid droplet in the airstream. So basically what this packing comparison shows, it compares us to the number 2 tri-pack, the number 3.5 Landtech, and then our number 3K. The number 2 tri-pack is similar to the 3.5 inch. That was just the number that they gave it back when they were developing the product. So what you can look at is you know, we don't have the highest number of surface area per cubic foot, but what we do have is the largest number of free volume, and then what that also correlates to is both those factors correlate to the lower the packing factor. And basically what that packing factor is, it's a correlation between pressure drop and the packing media itself. So we like to look at it as the lower the number, the better, and in the chart it shows that. But we've also got, you know, when it comes to performance, we have an abundance of performance curves that we've all developed in the field. We've done it through actual raw testing at our research facility. So basically, any of the designs that we put forth, we've got a leg to stand on. We know it's going to work. We've done the testing, and we've got full confidence in our design. So what I want to do is go through an example to show the Tellerette advantage. So basically, this is a general ventilation application. We're exhausting at about 50,000 CFM, ambient temperature, and HCl is our contaminant. We've got about 100 ppm, and we're trying to get 99% removal efficiency using a recycled water with a caustic injection. So like I said, we can do it in water only, but to get a bigger bang for the buck, we like to add a chemical to it and give the chem absorption. So basically, for the number 3K, this is going to put us in number 3K style because it's a larger CFM and it's going to be a larger diameter tower. Basically, we're aiming for 600 feet per minute. You can average between 500 to 600 feet per minute, but the number 3K was developed so we could increase the velocity through the packed bed. Your typical liquid rate is 6 GPM per foot squared, which is common. So when we look at the correlation, we're basically taking the CFM, dividing it by your velocity, and that's giving us a surface area, a diameter of the tower. So basically, we're looking at 83.34 feet squared, which puts us at about a 10 to 11 foot diameter scrubber for this particular application. So for a 10 foot diameter scrubber, we're looking at a 78.5 foot squared cross-sectional area. So it gives us a G rate, and what the G rate is, it's your CFM times your density times your correlation of minutes into hours, and then divide it by your cross-sectional area. So in this case, it's 2,800 pounds per hour per foot squared. So the L rate, same thing. We're basically getting GPM. We know we want 6 GPM per foot squared. We're doing some conversion factors that are getting us into the L rate of 3,000 feet per minute, feet per hour, or pounds per hour per foot squared. So this is one of the many curves that we have available, and we'll actually have a full package ready for download end of the month, early July, that you can sign up for on our website. That basically gives us all the operational curves for everything from the number 1 Tellerette all the way up to the number 3K. So this is one of the curves. We're basically looking at your G rate at 28,000 or 2,800, and then this is the pressure drop curve. So we know what the pressure drop is going to be at a 3,000 L rate, which in this case is going to be 0.28 inches per foot of packing. So as we look at the different packing different diameters of the towers, basically this chart below shows what we did for a 10-footer, an 11-footer, and a 12-footer. We've got all the cross-sectional areas. We've got the projected velocities. We've got the projected G rates, the L rates, And then the GPM below that, so you can see what the L rate correlates to. So, so for the 10-footer, the 3,000 L rate equals a 470 GPM recirculation rate. And it goes from 570 and 678 for the 12-foot diameter tower. So as you can see on that last line there, the pressure drop, it does increase as the tower goes bigger, but there is a cost associated with the bigger towers. So not only is there an actual cost of manufacturing, but there's also a cost for, say, the horsepower of the pump. So we may be at a 20 horse pump for the lower end, or sorry, 15 horse at the lower end, going all the way up to a 20 horse. So there's a value associated with going to a smaller tower. So now we got to figure out how big we want this packed bed to be. So we look at the number of transfer units. So in this case, since we're using a chemical to aid in the absorption, we can assume some of these slopes turn out to be zero. And it drops down to something very simple. Basically, you're looking at your natural log of your concentration in versus your concentration out. So we know we need to be a 99% removal efficiency. So we do the ln of 100 over 1, which gives us 4.61. And you can do that for, if you're looking for a basic NTU, as long as there's chemicals being absorbed with it, you can do a simple concentration of that. You can do a simple calculation for that. So this is another one of our fantastic curves that we can have for download. This is the HCl HTU curve. So you need to have your NTU and your HTU to give you the overall packed bed height. So once again, we go to the G rate of 2867, and we raise it up to the, I believe the triangle is the 3,000 L rate, and it correlates to a 1.15 foot HTU. So as we go on through and we look at our chart again, we can go through and plug in the NTU and the HTU, and we've also included a 1.2 safety factor. So basically what it's telling us is we can do the 99% removal efficiency in a 7-foot packed tower or 7-foot tall packed bed height for a 10-footer, an 11-footer, and a 12-footer. So we're looking at the overall pressure drop across the packing, across the inlet losses and external losses, and we get an overall pressure drop of 2.7 for the 10-footer, 1.9 of the 11-footer, and 1.5 for the 12-foot tower. Now what that does, that's less than an inch of packing, which is ultimately going to probably get you the same fan horsepower. And what you're looking at now is the cost of manufacturing for the 10-foot, 11-foot, and 12-foot, as well as the additional horsepower for the recirculation pump. So in this case, we've decided that, all right, we're confident that our scrubber, our Tellerette packing can do the 99% at the 10-foot diameter tower, and these are our final design conditions. So this little exercise kind of shows you where the real benefit of using the number 3K style Tellerette would be fantastic versus where you can actually increase your velocity and not design at your traditional 500 to 600 feet per minute. So one of the major curves that we put together over time is what this is showing is actually your pressure drop versus the efficiency for various filamentous style packing. So what we've done, we've compared the 3.5 land pack, the 3.5 tri-pack, which is the number 2, the number 2K style Tellerette, and the number 3K style Tellerette. And clearly what this shows is as you're requesting a higher efficiency, removal efficiency, the pressure drop doesn't increase as much for the 3K and the 2K style Tellerette as it does against some of our packing, our competitive packing. This is kind of the true telltale sign, and it basically shows that, yes, we do have one of the best, if not the best, packing on the market right now. So I want to go through a couple other examples that tout the Tellerette advantage. So this is if we're looking at designing a traditional tower with packing, with tri-pack, and then with saddles as well. So what the design basis is for this is that we're looking at 99% removal of ammonia at an L rate of 4,000 pounds per hour per foot squared. And our maximum delta P across the packing is 3.0 inches of water column. So what we've gone through all the calculations already, and to do that 99% removal efficiency, you basically need a 10.4 foot tall packed bed of Tellerette in a 7-foot diameter tower. To do the same thing with the number 2 tri-packs, you need an 8-foot diameter tower and 12 and a half feet of packing. And then for saddles, it's even a larger tower. And like I said, the reason it's a larger tower for the saddles is that you need to really slow down that air flow rate to get the proper transfer. So what this does is basically the figures at the top are a little dated but close. Basically, we're looking at your increased horsepower for the pump and the fan. So for the Tellerette, ideally you're about 10,000. For the tri-packs, you're about 11,000, and then for the saddles, you're about 12,000, a little over 12,000. But what the real thing is your relative capital cost. So that's assuming our design with the Tellerettes is a 1. It's basically a 1.3 factor to go to an 8-foot diameter tower. That's a little bit taller, and then it's a 2.12 factor to go to a 10-foot diameter scrubber that's even taller than the previous. So and then one of the other Tellerette advantages, the premises behind this one is we've got an existing tower. So a customer came to us and said, hey, I've got an existing tower. What do you got to do? It's an existing 7-foot tower. How much packing do you need to maintain a 99% efficiency for the ammonia application? And so basically, Tellerettes can do it in a 10-foot bed. The number 2 tri-packs can do it in a 15-foot bed, and the saddles are even higher at a 20.3 3-inch bed. And so, with that, you're also going to have increased pressure drop with the saddles, and then you're going to have an increased pressure drop with the tri-pack just based off the pack bed height. So there's a lot of real creative ways our engineers can tackle a situation for you and try to improve a customer's overall performance. So a couple of key advantages that Verantis and Dr. Teller, working via Seal Coat, came up with the first filamentous style of packing. And it's developed through continued development of the original design and improved capabilities with the creation of the number 2, the number 3, and the K series of packing. So with the Tellerette, you're going to get high efficiency, low pressure drop, and we try to pride ourselves in being the most economical solution for your needs. And like I said, that's not just on cost. It's reducing pressure drop. It's looking at the overall package. If we need to guarantee performance for you or a customer, we can absolutely do that. And we're definitely involved in retrofitting existing towers for the increased capability and higher efficiency, or both. So at that point, thank you everybody for sitting in, and we're ready to take some questions if you'd like to ask any. Oh, use the question box for the questions if you have it. Oh, we absolutely keep Tellerettes in stock. One of the questions was, do you keep Tellerettes in stock? We have a great relationship with our manufacturing here in Cleveland, Ohio, and we do warehouse Tellerettes. We've always got we don't always have, but we try to have 2,000 cubic feet of the number 2Ks and the 3Ks, and 500 cubic feet of the other Tellerettes. So I've got another question here for temperature limitations. And temperature limitations are based off basically what material construction. So for polypropylene, 180 to 200, but we've also designed, we also have Tellerettes with CPVC, glass-filled polypropylene, Kynar, and a handful of other various engineered polymers. The presentation, we have it. Do we plan on sending the presentation out? So we have it recorded, and we can absolutely send it out. Can we also? Are they going to have a place to download it at a later point in time?
Yes, it'll also be available on YouTube.
So the presentation will also be available on YouTube, and we'll have that ready to go. I have a question about moisture in the magna helix gauge lines. We've seen that, but that's anytime you're humidifying a gas stream, which is essentially what a scrubber is doing, there is a tendency to see that. One of the other questions I have is discussing the chemical conversion rate versus the absorption rate. Yes, basically liquid temperature, as the liquid temperature increases, the absorption rate becomes a little bit different. So it is important when we're looking at an existing design to know that temperature of the liquid. As you know, an example is if you're doing an ethanol scrubber, the cooler the liquid, the better the efficiency is going to be. So sometimes we've looked at adding a heat exchanger, like a plate and frame heat exchanger, to the recirculation loop, and that something as simple as adding that in increases your efficiency significantly through a packed bed. So we've got we got a question: with the additional surface area to the Tellerette, does it also increase fouling factors over the competitors? Well, the surface area, we don't have increased surface area. Basically, we've got the lowest surface area of a lot of our competitors. And so we don't see that problem as much as some of our competitors do. But it does happen. If the scrubber is not operating as it's designed to, say you're not throwing in the fresh water that's required, you'll absolutely get a salt buildup. So a lot of times the buildup is coming from, and this is for everybody's packing, not just ours, it's a lot of our competitors' packing as well. If there is plugging in the packed bed, it's basically because somebody decided to turn off the fresh water feed, which is very common because all the plant personnel are trying to save as much water as possible. So, but by changing that, you've got to know what kind of effect it's going to have. It's basically just like, you know, you start recirculating water with a bunch of solids in it. It's going to go somewhere. It's going to get plugged. So that's why the fresh water feed is extra important. We've got a question about how often a customer should change their packing. That's a loaded question. You know, we've got customers who change it every 6 months. We've got customers who haven't changed it in 20 years. The rule of thumb is every time the system's down, to take a look at it and make sure you have packing on hand if you need to replace it. But I also recommend putting it in a preventative maintenance every 1 to 2 years. But the key is just to make sure you have an eye on it. I've also got a question here about mist leaving the scrubber. So we've used packing as a mist eliminator. It can be done. We've actually on the curves that you can download, there's actually mist elimination capture curves for the number 1R and the number 2R style of Tellerette. Basically tells you what your collection efficiency is going to be at a G rate. With that said, there are a lot of great mist eliminators out there on the market. We manufacture a chevron blade assembly, which is basically your 3-bend with hooks. There's a bunch of mist eliminators out there with mesh pads. Chemry style is a great engineered specific mesh pad. So I would definitely recommend making sure that your mesh pads are sufficient, because the packing is not going to do it. You got to remember, it's a fully saturated airstream that's going out the top of the scrubber, so mist eliminator is extremely important. So I've also got a question about an HCl application for a vinyl plant. With all applications, they're very specific. We'd have to look at your conditions to make sure the pack bed is going to be sufficient for you. So if you have any specific applications, you can send it in through our website, and the right people here within the company are going to receive it. And Bill, I think I answered your question about the mist eliminators. Like I said, everything from packing to our Verantis chevron design, all the way up to various mesh pads like ACS and Chemry we've used for most applications. All right, so let's see here. And Bill's got another question here. How do you address permit compliance with pressure drop? That is a very tricky situation. Unfortunately, that's probably not the best way to set up a permit because especially with the engineered packings like the tri-packs, the Tellerette, especially the Q-pack, they tout the lack of pressure drop and the removal efficiency with the lack of pressure drop. So a lot of times those are industries that have been set in the ways, and you almost need to walk the engineer in charge of the permitting through the various steps. But that's a great question because we do see it, well, it doesn't have the best pressure drop. Exactly. That's what we designed it. That's the intent of it. So looks like that might be it with questions.